Most professionals treat Power BI as a digital canvas, a drag-and-drop visualization tool used primarily for making charts. This approach quickly leads to a brittle reporting environment. You experience lagging visuals, refresh times that drag on, and aggregations returning inconsistent totals. Graphic design and custom visual formatting cannot compensate for an unstable data model beneath the surface. When enterprise dashboards fail at scale, it is often because the creator prioritized the presentation layer over the engineering of the underlying data engine. Beneath the user interface, Power BI operates as a highly compressed tabular modeling engine built on analysis services. This infographic breaks down the unified pipeline. Notice the three distinct stages anchoring the bottom center: data models, DAX, and Power Query. Building a scalable system requires integrating these three layers: the transformation engine, semantic architecture, and context-driven logic. We are going to construct this system from first principles, beginning with the data structure rather than the visuals. Focusing on these tabular engineering requirements provides the foundation for models that must perform at an enterprise scale. The architectural build begins at the ingestion layer, where flat, raw data first enters the Power BI environment. This reference sheet outlines our first line of defense, Power Query, where structural transformations occur. Notice Change Data Type. Enforcing this reduces memory footprint and ensures faster execution. Also, Pivot Unpivot converts wide, human-readable flat files into tall, normalized columns for the tabular engine. This disciplined preparation prevents the issues caused by loading raw, dirty Excel sheets directly into the data model. Handling data shaping at the source eliminates the need to write complex DAX workarounds later in the build. A pristine upstream dataset is the physical prerequisite for a fast, responsive downstream report. Moving past ingestion, we enter the data modeling phase. In professional practice, many DAX calculation errors are actually the result of poor data modeling. This diagram illustrates the relational architecture required for Power BI, the star schema. At the center is the fact table, a repository holding quantitative metrics, foreign keys, and transaction records. Surrounding it are dimension tables containing descriptive attributes like dates and products. Filter arrows flow strictly outward, propagating from the one side of the dimension into the many side of the fact table. Restricting this cross-filter direction to a single pathway is necessary. Bidirectional filtering can create ambiguous data pathways and circular dependencies. This normalized structure reduces column cardinality, the number of unique values in a column, which allows for significant file compression. Adhering to a normalized star schema simplifies the model so that visuals render and refreshes execute without delay. With the physical structure in place, we apply dynamic calculations using data analysis expressions, or DAX. Writing effective DAX requires moving past static spreadsheet formulas to work with Power BI's dynamic context engine. The first paradigm is row context. Think of this as a scanner iterating horizontally across your data. It steps through records one by one, used by iterator functions like SUMX. The second paradigm is filter context. As a user interacts with a dashboard slicer, this funnel subsets the data before any mathematical operation is performed. Filter context acts as the global environment. It defines which data points are included in the calculation based on the current report state. Confusing these two environments results in metrics that may appear correct but fail under detailed scrutiny. Distinguishing between row and filter context is the requirement for building accurate enterprise BI architecture. To control the environment, you use Calculate. As this guide details, it programmatically overrides the user's existing filter context. The filter argument forces a specific requirement onto the data model, regardless of selections made on the report page. This capability is what enables standard time intelligence within the model. By manipulating the context, functions like total YTD, or same period last year, extract comparative trends, answering questions like year-over-year variance. To optimize these calculations, use dynamic DAX measures instead of static calculated columns. This approach preserves available RAM. You can further improve performance by disabling the auto date time setting to remove unnecessary background tables. When driven by the calculate function, DAX transforms a static, lifeless database into an interactive, context-aware decision engine. With the DAX logic complete, the high-performance semantic model is ready for production. Publishing to the Power BI service transitions the model to a governed enterprise asset. Notice nodes 12 and 09. Secure gateways allow for automated scheduled refreshes, while row-level security restricts data visibility based on user roles. Automated distribution and robust security are only possible because the entire back-end engineering was executed to strict professional standards. The mechanisms that allow Power BI to scale remain invisible on the dashboard surface. Long-term scalability integrates sanitized upstream data, a strictly normalized star schema, and context-aware DAX evaluation. Adhering to these architectural requirements eliminates reporting ambiguity and builds trust in the final numbers. The entire Power BI ecosystem functions as a rigorous analytical engine that is specifically designed to drive confident, data-backed business action.